right, so we're going to prove Binet's formula. We're going to let alpha be the positive solution and beta be the negative solution to the equation x squared is equal to x plus 1. You could solve for these to get the value of alpha is 1 plus the square root of 5 over 2, and beta is equal to 1 minus the square root of 5 over 2. We want to show that for all natural numbers n, that the nth Fibonacci number is equal to alpha to the n minus beta to the n over alpha minus beta. So let's go ahead and do this proof, and we're going to do this by PCI, okay? Proof by the principle of complete induction. It's going to start off like all the other inductions. We're going to have our base step, okay? So we're going to consider the statement involving 1. So we have the first Fibonacci number, which is equal to 1, right? And let's go ahead and see, well, alpha to the 1 minus beta to the 1 over alpha minus beta. Well, that's just alpha minus beta over alpha minus beta, which is 1, right? Which is, of course, the first Fibonacci number. So this checks out, right? Okay, so we can go ahead and move on to our induction step. Induction step. So for the principle of complete induction, we're going to suppose S of 1 is true, the statement involving 2 is true, the statement involving 3 is true, all the way to the statement involving k minus 2 is true, and the statement involving k minus 1 is true. All right, so that's how the principle of complete induction works. You suppose all the previous terms are true, and then assuming that, you want to prove that the next term is true, which in this case would be k, right? That would be the next term in the sequence. Or all k contained in the natural numbers. Okay, so now we're going to consider the kth Fibonacci number, right? Okay, well, we know the Fibonacci numbers are defined by the sum of the two previous terms. So this is going to be f k minus 1 plus the k minus 2 Fibonacci number. We know the kth Fibonacci number is the Fibonacci number before k plus the Fibonacci number before two entries before k, right? All right, so now what we have here is, remember, in our induction step, we suppose that all of the statements were true, including the statement involving k minus 2 and k minus 1. So from our assumption, this means that the k minus 1 Fibonacci number is equal to alpha to the k minus 1 minus beta to the k minus 1 over alpha minus beta. And the k minus 2 Fibonacci number is equal to alpha k minus 2 minus beta k minus 2 over alpha minus beta. Okay, so the good thing about this is we have a common denominator, right? So I'm going to put the alphas together. So this will be alpha to the k minus 1 plus alpha to the k minus 2. And then what I'm going to do here is I'm going to do minus, and then I'll have beta to the k minus 1 plus beta to the k minus 2, right? Because both of these are negative, and if I were to combine these fractions together, I would have negative beta to the k minus 1 and negative beta to the k minus 2. So I could factor out the negative to have this, right? And that's all over alpha minus beta. So remember, I want to prove that the kth Fibonacci number is equal to alpha to the k minus beta to the k, right? So I can actually get those out of this. So I know this is equal to alpha to the k. So if I were to get alpha to the k, alpha to the k times what gives me alpha to the k minus 1? Well, that would just be alpha to the negative 1, right? Alpha to the k times alpha to the negative 1 is alpha to the k minus 1. And then plus, and then alpha to the k plus alpha to the negative 2 gives me alpha to the k minus 2. So I can factor out that alpha to the k, and I'm left with this. And I can do the same thing over here. Beta to the k times beta to the negative 1 plus beta to the negative 2. And that's all over alpha minus beta. Now, I would be done if alpha to the negative 1 plus alpha to the negative 2 is 1, right? And I would be done also if beta to the negative 1 plus beta to the negative 2 was also 1. So now I need to show that both of these are equal to 1, and then I'm done with my proof. Okay? So alpha to the negative 1 plus alpha to the negative 2. Remember, this is equal to 1 plus the square root of 5 over 2, and this will be to the negative 1, right? Plus 1 plus the square root of 5 over 2 to the negative 2. All right, so now I'm going to deal with these inverses. So I know with inverses, I can just flip them, right, to get rid of those inverses. So this will be the same as 2 over 1 plus the square root of 5, right? Plus, but this one has a negative 2, so I'm going to flip it and still keep that 2, right? So this will be 2 over 1 plus the square root of 5, and this will be squared. All right, so this is equal to, let's see, 2 over 1 plus the square root of 5 plus, so this times itself is 4 over 1 plus the square root of 5 squared, right? So that means I have to multiply top and bottom here by 1 plus the square root of 5, so I get a common denominator, right? So this will be 2 times 1 plus the square root of 5 over 1 plus the square root of 5 squared plus 4 over 1 plus the square root of 5 squared. All right, now this is equal to, so let's see, now let's go ahead and distribute, right? Because we have a common denominator. So this will be 2 plus 2 square root of 5, right? Blah, blah, plus 4. And that'll be over, so these are the same, so let me go ahead, well, I'll just leave it like that right now. 1 plus the square root of 5 squared. And then 2 plus 4 is 6, so this will be 6 plus 2 square roots of 5 over, so this will be 1, right? 1 times 1, 1 times the square root of 5, and then square root of 5 times 1, so that'll be plus 2 square root of 5. And then square root of 5 times square root of 5 is 5. So this equals 6 plus 2 square root of 5 over 6 plus 2 square root of 5, which is indeed 1. So we've shown that alpha to the negative 1 plus alpha to the negative 2 is in fact 1. So now we just have to show that beta to the negative 1 plus beta to the negative 2 is 1. So beta, beta to the negative 1 plus beta to the negative 2. So remember, this was the negative solution, right? So this was 1 minus the square root of 5 over 2. So this is the same thing as 1 minus the square root of 5 over 2 to the negative 1 plus 1 minus the square root of 5 over 2 to the negative 2. So we're going to do the same thing as we did before. this is, so we can just flip these because that's the inverse. So this will be 2 over 1 minus the square root of 5. And then this will be plus, and since this is negative 2, it'll be 2 over 1 minus the square root of 5 squared. Now this times itself, this is going to be equal to 2 over 1 minus the square root of 5 plus 4 over 1 minus the square root of 5 squared. Right? And then now we have to get a common denominator. So this is equal to, so 2 times 1 minus the square root of 5 over 1 minus the square root of 5 squared plus 4 over 1 minus the square root of 5 squared. Okay, so we can combine this now. So this will be 2 minus 2 square root of 5 plus 4 over 1 minus the square root of 5 squared. And now 2 plus 4 is 6. So this will be 6 minus 2 square root of 5 over, so 1 times 1 is 1. 1 times negative square root of 5 is negative square root of 5. Negative square root of 5 times 1 is, so that'll be minus 2 square root of 5s. And then negative square root of 5 times negative square root of 5 would be positive 5. So we'll have 6 minus 2 square root of 5 over 6 minus 2 square root of 5. So that over that is just 1. So we've proven that alpha to the negative 1 plus alpha to the negative 2 is equal to 1, and beta to the negative 1 plus beta to the negative 2 is 1. So we can go ahead and go back to here. So let's go ahead. So this implies that the kth Fibonacci number, remember, this was equal to alpha to the k times alpha to the negative 1 plus alpha to the negative 2 minus beta to the k times beta to the negative 1 plus beta to the negative 2. And that was all over alpha minus beta. And we just proved that alpha to the negative 1 plus alpha to the negative 2 was 1. So this will be alpha to the k times 1 minus beta to the k, and we proved that was also 1 over alpha minus beta. So this is equal to alpha to the k minus beta to the k over alpha minus beta. So we've shown, right, this implies that the kth Fibonacci number is equal to alpha to the k minus beta to the k over alpha minus beta, which is exactly what we wanted to show, right? Assuming that the statement was true for all of the preceding terms, right, up to k minus 1, we've shown that it was true for the next term, right? And of course, if Fibonacci, we just use the previous terms, right? But complete induction, there are some problems where you have to use all the previous terms, right? But we were able to prove this using the principle of complete induction. So this implies that the statement involving k is true. Therefore, by PCI, the principle of complete induction, for every n contained in the natural numbers, the statement involving n is true. AKA, we proved that for the nth Fibonacci number, it's equal to alpha to the n minus beta to the n over alpha minus beta, right? And that is the proof of Binet's formula.